Thank you, and thank you to the Government of India and USAID and GIZ for putting on this, for sponsoring this fabulous conference. I'm going to be talking about the renewable energy grid integration study that we recently completed. This is under the sponsorship of MOP and USAID, along with the 21st Century Power Partnership, World Bank, and SMAP, and prepared by several folks in this room, David, Ranjit, Mr. Suni, Mr. Baba, so represented by POSICO, NREL, and Berkeley Lab. So we were looking at two core questions. If India develops the 100 gigawatts of solar and 60 gigawatts of wind energy, how would the system operate in 2022? And what can policymakers do to lower the cost of operating this system and better integrate the renewable energy? And so I want to note that this is an operational study. We are not looking at how do we get to 2022 or what's the right set of investments. We are diving into the year 2022. All those investment decisions have been made already. And we are looking at how do you operate the system most effectively. One of the aspects that I'm most proud of on this study is the extensive stakeholder engagement that we had. We had the technical review committee. We did this at 4 stages of our study from beginning to end and in 3 cities. So we had quite a number of experts, many of whom are in this room today, to provide us guidance to make sure we were asking the right questions, finding the right data, and interpreting the results correctly. To give you a brief overview of what we did, we built an operations of today's power system, validated it, and then we looked ahead to 2022 to add the load and the generation and transmission, including all the RE. And then we simulated the operation of that system in using Plexus, which is a production cost model. We had 5 scenarios that we looked at. The main one in yellow was this Government of India target, but we also used for a base comparison, not adding any renewable energy. That's our no new RE scenario. And then we also looked at, more wind instead of more solar, and looked ahead at the 150 gigawatts solar, 100 gigawatts wind, which has now already been alluded to as perhaps being here in 2027. So we looked at that using 2022 demand, but still capturing some of those high penetrations. But today I'm only speaking about the main Government of India target. Another feature of what we did in this study is to use high quality data. So particularly renewable energy resource data. Because we're talking at such high numbers of capacity of wind and solar, we wanted to make sure we are capturing the smoothing effect that comes when we add on this much variability in diverse locations. So we used unique weather properties for the full year for each location for wind and solar. And we also had very detailed generator properties, a lot of transmission information, which we constrained state to state, and in some cases within the state. And then here's our 2 versions of the transmission that we looked at. The left is the national study, and this is the one I'm going to be talking about today. But here we simplified transmission within the state so that we assume that transmission within a state would not be an issue. And we were really looking at the big picture questions about what are the main drivers for RE curtailment, where do we, how does each state contribute to an overall India-wide system balance? What's the role of coal flexibility? This was a simpler model to run, so we could run a lot of different scenarios and sensitivities on this one. Then we also have a regional study where we added, we enforced transmission lines down to the 400 kV, to all relevant 400 kV lines within the southern and western regions and the state of Rajasthan. And so here we didn't do as many different scenarios, but we really looked into what's going on within the state and what's the impact of adding this renewable energy. Yeah, it's working. Okay, so here is a visualization. This is on a website. I don't have the URL on here, but you can Google it, I'm sure, and find it, or just check with me later. But what we are looking at is the results. So we put all that data into the model, we ran it, and this is the visualization spitting out the results for every 15 minutes of the year. And right now we are looking in July, so the monsoon period, And what we are seeing with these colored dots is what is the generation in each state, as represented by generation type, the colors, that's being used to balance the system. And so we can look, so right now it's nighttime, the sun's about to come up, the dark black is coal, the gray is coal, the dark blue is wind, and then now that the sun's coming up, you're going to see the yellow solar come on the system. So you can see that this is July 2nd now. The wind profile for the whole country is pretty smooth. It does vary seasonally, of course, and then as you get into smaller locations, that variability is much greater. So like if we looked at just Tamil Nadu, like the examples we were hearing this morning, you would see more variability. But when you look at it aggregate over the whole country, the wind is smoother, the solar profile tends to have pretty predictable change in variability. And then we also see in red is curtailment. So we do see curtailment, particularly in the monsoon season when wind and solar are both high, and we see it midday, typically. So what we can do with all those data points from all the 15-minute time periods is learn about what are the annual results, what are the challenges that we see in the system. And one example is that we have learned that 175 gigawatts of renewable energy can meet 22% of India's annual electricity demand with minimum RE curtailment. This map shows by state what the renewable energy penetration level is as a percentage of generation in green and as a percentage of consumption in blue. And you can see that if we get a lot of renewable energy growth in the south and in west as we expect, some of these states are going to be looking at annual penetration levels around 50%. We also saw, because you're having so much more renewable energy, there's going to be less coal generated as a result, and we do see carbon dioxide emissions reduced by around 21%. We can also see impacts of this renewable energy at a daily level. And this is a picture that shows the load curve on a monsoon day in 2022. So the black line is the load curve. And if we were to use all the wind and solar generation, the rest of the conventional fleet would need to meet that orange line. That's the net load curve. So that's the net load is what is needed to be met by the coal, the hydro, and other sources. We can learn a few things by looking at the shape of this. One, wind, as I was showing in that other picture in the visualization, wind is available day and night, so it lowers the overall amount of capacity that's going to be needed on the system from coal and such. And then also you can see it dip down during the day when the solar generation is on. We did find that the system was able to manage all the ramp rates at these different time periods throughout the year, so ramping was not a constraint, but we did see a great need for that flexibility of the coal plants to be able to manage this dip during the day. And we can see this in this chart. I'm going to skip this for time, but just really quickly on the right side, that's our high renewable future, and the thick black line is the commitment of the coal capacity, and then the shaded area below it is what is the dispatch. So you can see that instead of the no new RE, which is on the left, we are seeing a much stronger dip, a daily dip in what our coal generation needed. This is all India. Skip that one. So as a result of operating our coal plants at, at lower dispatch levels and lower commitment, we do see a change in plant load factors and the PLFs of the plants. So on the left chart, each of those dots represents one coal unit in India sized according to its actual capacity size, and then its position on the vertical axis is its plant load factor. Right, like in our no new RE scenario, the plant load factor for coal on average was 63%, and it falls to around 50% in the high renewables situation. So this is, you can see here is the high renewables, and it's not evenly distributed. Some coal plants are more efficient, have lower variable costs, are operating at much higher PLF levels. But you can see at the bottom, there's quite a number of plants that operate either very rarely or are never economical to turn on during the course of the year. So that has commercial implications, having the lower PLFs. And so we wanted to look at, well, what would be the impact in terms of RE integration if we were to remove the coal plants that had a PLF of 15% or less. So we retired those 46 gigawatts of coal, which is the equivalent of 20% of coal capacity, and we learned that it did not affect system operations. The RE curtailment was the same, it didn't go up. We were still able to meet load. All of the 46 gigawatts of coal had only contributed 1% to generation, so removing that 1% was easily made up by the other resources on the system. So what we learned from that is that a system with 175 gigawatts of renewable energy could support some combination of higher demand growth or retirements of generation. And then we also looked at, well, what could we do to operate the system more cost effectively and also reduce the RE curtailment? And we had discussions this morning about the costs associated with adding RE to the system. And I also want to note that there are also potential savings that we can access to. So I'm not dismissing the cost, but there are also ways to save money so that the consumer in the end is still well off. So one of the biggest drivers to reducing the costs on the system is better coordination on scheduling and dispatch. And Dr. Chatterjee talked about some of the efforts on that front in the market perspective. The way we did our regular modeling on all our base cases was that we simulated each state doing its own scheduling and dispatch with some trade, of course, but still not balancing areas is essentially trying to mimic at the state level. So we looked at balancing at the regional level and also at the national level. When we balance at the regional level, that can save 6,300 crore annually. So it's almost $1 billion annually of savings by operating the thermal fleets more effectively, accessing the lower cost thermal fleets, and then turning off some of the ones that are more expensive. In terms of the drivers for RE curtailment, we found that the minimum generation of the coal plants were the biggest drivers. So we looked at a variety of metrics on coal flexibility. We looked at minimum up-down times, what the ramp rates are, and none of those had as much impact as minimum technical generation. So first, our main scenario is 55%, which is the CERC requirements for central plants. But we did look at, well, what happens if we have it at 70%, and then the RE curtailment increases to 3.5%. And we also looked even down to 40% and a few other combinations. So that chart where you can see that coal dip, that is what is essential for managing that solar, the whole system when that solar generation is on during the middle of the day. We looked at batteries as well from a scheduling and dispatch perspective. So batteries have a lot of value for all kinds of aspects on the power system, ancillary services, capacity, transmission constraints. We didn't look at any of that aspect, but we did look at the energy value of the batteries. So we added 2.5 gigawatts of batteries and wanted to see, well, where is the value of these batteries? And as we expected, it charges during the day when you have that, plentiful solar and wind generation and other sources online. But there's also a lot of coal generation online too. And then it discharges in the evening to meet peak load. Because of the losses in terms of battery efficiency, we ended up having the same amount of coal generation with and without the batteries. Because it's charging during the day, it is increasing the coal consumption during the day, and then when it's discharging in the evening, it's offsetting that coal generation. So it ends up being about net the same. We did reduce RE curtailment, but the system costs were about the same, and same with carbon dioxide emissions. So the sort of what we've learned from that is when we're thinking about batteries on the system, it's important to be thinking about the other sources of value for it. And then finally, we looked at low and high hydro years in terms of its effect on RE integration. So low and high hydro can have differing impacts to RE integration. When you have more hydro, that might be more of a balancing resource available, but also if you have more hydro, you might have more must-run times for the hydro in terms of generation, and therefore reduce the flexibility on the system. So it can go either way. We looked at two extremes of hydro years, and we did not see an impact on RE curtailment. We did see the costs go down when you have more hydro, which is expected because hydro is a free fuel resource, and it goes up when we have decreased hydro output. But from an RE integration perspective, it seems that you can have a variety of hydro years and not have it affect the ability of the system to integrate RE. So finally, I want to echo the point that Mr. Baba made and Mr. Verma, that India's power system has significant physical flexibility, the technical flexibility is there, to integrate 175 gigawatts of RE within the existing plans. However, harnessing this flexibility is the key challenge. And so Mr. Baba talked about, the commercial aspects being key, and so that comes out in this paper. There needs to be the appropriate combination of operating rules, market rules, regulations to make sure that the incentives or requirements are there for coal generators and RE generators, et cetera, hydro, to provide the flexibility when it's needed so that the system operator can access it. So we know it's out there, but we have to make sure all the commercial and institutional sides line up. So for example, number 3, we can consider ways at the state level to compensate coal plants for operating flexibly. And then finally, this is more of a topic for our volume 2, which is the regional study, but we did identify the need for planning to identify optimal locations for new RE and associated inter and intrastate transmission. So in that in-depth transmission version of our RE integration study, RE curtailment numbers can be very sensitive to whether that RE is being evacuated and flow on the grid. So that is hopefully also under consideration from many of you. Okay, thank you very much. I'm on time.